1.5. Finishing up 1.5, there's one more thing called parametric curves. Okay, so kind of a strange thing, or maybe it's a new thing for you. So it's like this. So you have two functions. So anyway, definition: given two functions, f and g. So f and g, both going from R to R, say. We can consider a new function, gamma, going from R to R2. Okay, so it goes from R into the plane. So So gamma is going to go from R, the real line, into R2, right, the plane. Okay, and the way you create it is you make it out of f and g by saying gamma takes a point to the point on the plane where the coordinates are f and g. Okay. The coordinates of that point are f of t, g of t. Then we say the image of gamma is called a parametrized curve. Parametrized curve, or curve parametrized. Sometimes curve parametrized by x equals f of t, y equals g of t. Okay, so let me give some simple examples. Okay, so one, if f of t is t and g of t is t, okay, here's a simple example. F of t is t, g of t is t, then gamma, what's gamma going to do? It'll take t to f of t, g of t. So just t comma t. Right. It'll take the point t to the point, it'll take the number t to the point t comma t. Right. So what's the picture of that? Right. At time 0, right, when t is 0, you start off at 0, 0. Right. When t is 1, where are you? You're going to be at 1, 1. Right. When t is 2, you're going to be at 2, 2. Right. When you're at -1, where are you? -1, -1. And you see what this does. So as time goes forwards, usually people think of t as time. As time goes forwards, this thing walks in this direction on the line y equals x, right? As time goes backwards, it walks in this direction on the line y equals x. Okay, so this is a parametrization of the line y equals x. So this is a parametrization of the line y equals x. This is one parametrization of the line. Okay. Now, Elise, do you have a question?
Sorry, I was just curious what the word was when it says the image of.
The image of gamma is called a parametrized curve.
Oh, okay.
Sorry. Called a parametrized curve. Okay, everyone all right with that first example? Right, pretty straightforward. Suppose I have something like this. Gamma of t is t squared comma t squared. What does that parameterize? What kind of a curve do you get as t goes through time? Well, let's think about it, right? At time 0, where are we?
0. Would be the same thing as before. 'Cause
Almost.
It's still the same.
Almost the same, right?
It would just be. Oh wait, no.
Something's different. Something is different. So as at time 1, where are we?
It stays positive.
Stays positive. Okay, so at time 1 we're at 1, 1. At time 2, where are we? 4, 4, right? Time 3 we're at 9, 9, right? Et cetera, et cetera. So as time goes forward, it goes off to infinity, right? It goes off to infinity along this direction, the same line, but the same line, right? Okay. But it goes at a different speed, right? You notice that it goes a lot faster, right? At time 3, at time 2 we're only here. At time 3 we're only here, but for this guy, at time 3 we've moved out a lot faster. Okay. Second thing, where are you at negative 1?
You're still one.
Right, you still go this way. So if you go forwards through time, you go like this. You reverse time, you'll come back to here, and then you'll bounce back and go up again. Right? Okay. Whereas for the other one, this is basically a one-to-one relation, right? You go forward through time, you go backwards through time. This, right? For this one, you go forwards through time, right? And you reverse time. It goes quickly and then slows down, and it starts off slow and then speeds up again. Okay. And so the behavior is different. Okay. What if I have something like this? Gamma of t is, say, t comma t squared.
I understand. Why doesn't it go in that direction?
Why?
Like, because it's negative 1
Yeah.
is 1, so if you're plotting it. when you
Yeah,
go-
negative 1 is going to be 1 comma 1, right? Right.
Okay.
Negative 2 is going to be 2 comma 2. It's actually sort of an even function, right?
Okay.
Though we don't really call these guys oddity. Annalise, do you have a question? No. Okay, what about this one? Gamma of t is t comma t squared. Don't load it up. Think. Okay, turn to a neighbor, say it's something or other. Okay, what is it? What is it? Shannon.
Would it be like a positive
A positive curve? What kind of a positive curve?
like one side of a parabola?
One side of a parabola. So let's think. At time 0, we're at 0, 0. At time 1, where are we? We're at 1, 1. At time 2, we're at 2, comma 4. Right? At time 3, we're at 3, comma 9. Right? 3, 9. So that's, right? We're going up like this. We're tracing out that part of a parabola. Right? What happens as time reverses? We're going to get the other half of the parabola. We'll get the other half of the parabola. So this is a parametrization. Right? This is a parametrization of y equals x squared. Right? Of the parabola y equals x squared. Isaac.
To be able to do this, we only need the parameterized version of it, and then we can just plug in and get a set of numbers that we can really graph.
Well, so plugging in gives you some sense of what it is, right? And if you think about it, so maybe I start plugging in, I think, oh, this thing looks like it's a parabola, right? I think it looks like it's a parabola, and then you look at it and you think, well, look at this thing. The y coordinate is the square of the x coordinate, right? The y coordinate is the square of the x coordinate, right? The y coordinate is the square of the x coordinate. Here, the y coordinate is the x coordinate. The y coordinate was the x coordinate, right? And so you see, everything here must lie on that parabola, right? So plotting in points gives you some hint, right? And then thinking gives you like confirmation. Okay. Last one. Suppose I have gamma of t is cosine t sine t. Yes, Becca.
Why do we draw the axis with the on the side to the left if we don't plot points to find the what is the purpose of the axis?
No, I'm not following your question. Say it one more time.
What is the purpose of the axis if we don't plot points? How does it serve as a reference?
Well, I mean, we are plotting some points.
Okay, how do we plot points in the parametric curve? How would we?
So for example, you could say, well, where are you at particular times,
Okay.
right? At time -1, at time -2, well, I'm going to be at -2, 4, right? -2, 4. So you come up your thing. You say, well, at time -2, I'm at 4. This sort of thing, and that'll give you some sense of it. Right? But in some sense, you don't need to do that if you think about it, right? If you think about it, you say, oh, look, the x coordinate. I'm sorry, the y coordinate is the square of the x coordinate,
Oh.
right? And so you know this is a parabola. You don't need to plot any points. Okay. This last one. Anyone have an idea? Cosine t sine t.
Can I ask?
Yeah, Nico.
one question?
Yeah.
So when you're saying like the gamma
Gamma? Mhm.
t, is that the same? And then is that the same thing as saying like f of t equals cos t?
Yeah. So this is an abbreviation. So f of t is cos t. G of t is sine t. Right. Gamma of t is your f of t. F of t, g of t. Yeah, I should say that people often, instead of calling these f and g, call them x and y, because one is the x coordinate, the other is the y coordinate. Right? But it doesn't matter. You can call them whatever you want, a and b. Okay, does anyone know what this is? Anyone have an idea? Win?
Would it be tangent t?
No? Let's think. At time 0, where are we? Allie?
Well, isn't cosine usually equated to x and sine?
Of what?
Like on a graph, cosine is usually x
You're sort of in the right area.
and sine is y.
Does anyone know what we're getting closer to? The circle, right? The circle, right? What's cosine of 0? 1. What's sine of 0? Right? So at time 0, cosine, you're going to get cosine 0, cosine 0, sine 0, right? 1 comma 0. What about at time pi over 2? What's cosine of pi over 2? 0. Right? Sine is 1, right? We're here, right? At time pi, where are we? We're here. At time 3 pi over 2, where are we? We're here. And in between, right, if we look at cosine and sine of pi over 4, right, that's root 2 over 2, root 2 over 2, right, et cetera, et cetera. So this is, if you know what the cosine and sine are, right, then you recognize that this is just tracing on a circle. Okay, so this is a parametrization of the unit circle. Unit circle. Isaac?
It really feels like I'm just plugging in for the values and then getting them out. So what purpose is it calling it a parametrization rather than just a function?
It is a function. It is a function. Yeah. It's a function, but it's a function that's related to a particular curve. Okay, and so what you say is that I have this curve, and this guy here parametrizes that curve. This thing is called the parameter. The t is the parameter, and as the parameter changes, you trace out the curve. So it's like to each point on the to each point t, it corresponds a point on the curve. Okay, so it's called that's why it's called a parametrization of it. You've taken your curve, which was one thing, and you've basically associated numbers to each part of it. Okay, so actually, the last section has to do with these trigonometric functions and stuff. So let's get to that now. Yes, but
Isn't the definition of a function that each point has a value associated with it?
yes.
So what's the difference between that and it being parameterized?
So it's true. I mean, this is a function, right? R to R2. This is a function. It's true. It's a particular kind of function. The image of it is a curve, and we say that it's a parametrization of that curve. But I'm not going to say that it's not a function. It is a function. But this kind of function is called a parametrization also. Okay. So 1.6. Other questions? Other questions? Other questions? Okay. Trigonometric functions. Okay. So we'll make that. We'll make this connection. This last example a bit clearer once we get to the right part. Okay, but let me just start off with a question. Where is the 360 in 360 degrees? Okay. If you have a circle, right, and somebody says, oh, 360 degrees, the circle is 360 degrees, and an alien comes from another planet and says, I see a circle, I don't see a 360. Why do you call this 360? Why do you call this 360? Isaac?
It's 360 degrees from the origin, from wherever you start. Like, if you go all the way around from wherever you start, it's 360 degrees.
Okay, I'm an alien from another planet. Why do you call that 360? Why didn't you call that 370? Why don't you call it 100? You humans seem to like multiples powers of 10. Why not 100? Why not 1,000 or 1 or something like that? Why? Yeah, Becca.
The Babylonians like powers of 6s and 12s and
That I think is the right answer. You say the Babylonians. It's because of the Babylonians. Yeah. So there's a historical reason to this, and it's associated with the calendar actually, right? About 360 days in a year. Right, for the Egyptians, there were 360 days, and then there are 5 extra days. Right, there are 5 extra days tagged on at the end, so that a particular goddess could give birth to her 5 children, because she was cursed not to give birth to them within the year. So they found this out, like they added 5 days onto the year. Okay. So it goes back to sort of ancient. Astrology or astronomy. Where's the 360? It's because of our solar system. That's, I think, the real answer. You'd say, well, Mr. Alien, take a look at the length of our year. You'd say, oh, okay, now I get it. Well, but what about that 5 extra? Yeah. Okay. So the 360 is sort of arbitrary. That's the point here. It's not arbitrary. It has to do with our solar system. But if you were from a different solar system, well, then would you change your number? Okay. So instead of using this sort of arbitrary system, what you do is use radian. One uses one uses radian measure. Okay, and instead of calling the circle 360, the circle is 2 pi radians. Okay, 2 pi radians. Where's the 2 pi? Where's the 2 pi? The circumference, Kayla? Yeah, the circumference of the unit circle, right? The circumference of the unit circle. You'd say, well, if I'm looking at this angle, this arc length here is 2 pi, right? This arc length here is 2 pi, and that's why I call that angle 2 pi, right? And an alien would say, oh yeah, we do too, or something like that. Yeah, I mean, because this would actually make sense no matter where you're from, right? You say, well, we're going to base the angle on the length of the arc. So for example, right? If I'm looking at this arc, right? The length of this arc is pi over 2, and so I call this angle pi over 2. Right? This angle is called pi over 2 radians. Right? This angle is called pi radians. Blah blah blah. Why? Because if you look at the unit circle, then the arc length, the length of the arc subtended by this angle is that length. Okay, right, so that's radians, just to remind you what radians are. Right, yeah, this is, right, if I have something like this, halfway here, then that's pi over 4 radians. Right, 45 degrees is pi over 4 radians, et cetera, et cetera. Okay, now review of the trigonometric functions. Okay, so start off with a unit circle. And suppose this angle is theta radians. Okay, so theta radians. So we're always going to be in radians in this course. Whenever I say an angle, unless I say degrees, it's radians. Okay, and look at where this ray hits the unit circle and call that point P theta. Okay. Point at angle theta. Okay. We define the cosine of theta as the x-coordinate of P theta. We define the sine of theta as the y-coordinate of P theta. Right? Okay. So, for example, right, if somebody says, what's the cosine of 0? What's the cosine of 0? Well, I'm going to look at P0. P0, and the coordinates of that are 1, 0. Right? So that tells me that the cosine of 0 and sine of 0 are 1 and 0 respectively. Cosine of 0 is 1, sine of 0 is 0. Right? If I say, what's the, if I look at, the coordinates of P 3 pi over 2, I see that that's 0, negative 1, 0, negative 1, and that tells me that that cosine of 3 pi over 2 is 0, and sine of 3 pi over 2 is negative 1.
In that one, wouldn't the cosine be 1 then, because it's the x-coordinate?
The cosine is 1 and the sine is 0?
Yeah, because you said it's the x-coordinate.
Yeah, the cosine is 0. Cosine is 1 and the sine is 0.
Why does it say 0 next to
I'm not following. So here we're looking at P0, right? You see that the coordinates are 1, comma 0. 1, comma 0, right? So that tells me that the cosine of 0 is 1, and the sine of 0 is 0.
Oh, yeah, I think, okay, sorry. Okay, yeah.
Right, this is going to be cosine 0, sine 0, right? So cosine 0 is 1, sine 0 is 0.
Yeah, all right.
Okay.
Awesome.
Right. Okay, so this is how you define the cosine and the sine. This is how you define the cosine and the sine. The cosine is the x-coordinate of the point on the unit circle that you get by running a ray from the origin at that angle. Okay, right? In English, right? Cosine theta is the x-coordinate of the point on the unit circle where a ray at angle theta intersects that circle, right? And it's easier to just say it like this, right? Here's the look at this point. Cosine is the x-coordinate, sine is the y-coordinate, right? Does this help you? I don't know. Right? And then sine is the y-coordinate. Just out of curiosity, does it help you to see it all in English? Or does it help you any more than what we said already? Close your eyes for a second. No, keep your eyes open. Raise a hand if this actually writing this out actually gave you something more than wasn't here. Interesting. Okay. Yeah. It's the same thing, right? It's exactly the same thing, right? The cosine is the x-coordinate of P theta. P theta is the point on the unit circle where this ray intersects the unit circle, right? So it's the same thing, but it's interesting that it actually gives you something. Yes. Elise.
So how does that relate to, you can only use radians for that, right?
That's right. It doesn't work for degrees.
So it doesn't.
Whoa. I'm sorry.
Well, not for degrees, but can you relate?
I'm sorry. It does work for degrees, right? You could say, what's the cosine of 0 degrees, and it's just going to be this thing.
But how can you relate that to like a regular point? Like if you had the same point, but if you were to say it in a different way, like if you had the point like 2, 1, would you be able to relate that to cosine and sine? Because it's the same point, you're just saying it in a different way.
Oh, I think you're asking if you wanted to find the cosine of that or something like that. The cosine.
Yeah.
But suppose you had a triangle and you wanted to find the cosine of that.
Right. So if you just have if you have a point, but you want to say that in cosine and sine.
It'll give you the same thing, of course.
Okay.
It'll give you exactly the same thing. Why? Similar triangles. So, right.
Yeah. Okay.
By similar triangles, it's the same thing. Yeah. Yeah. So yeah, it's the same thing. If you were introduced to cosine and sine via triangles, that's fine. But this is actually the sort of like the right way to do it. The right way to talk about cosine and sine. Yeah. For example, when you do that stuff using triangles, how do you know if it's plus or minus? You sort of have to remember, right? Oh, sine is positive. Where is sine positive?
In that, in the upper left.
Here and here, right?
Left.
And cosine is negative where?
Yeah, and-
Cosine is negative over here,
Yeah.
right? Right. But now that's completely obvious, right? The cosine is the x-coordinate. The x-coordinate is positive over here. The x-coordinate is negative here.
All students get calculus.
Yeah, you see, I don't want to remember anything like that. I don't want to remember anything like that, right? That's extra information. If I know what the cosine is, I don't want to clutter my brain with all sorts of mnemonics, right? That's too slow. What's that? That's your childhood? Yeah. Welcome, welcome to adulthood. Yeah. So here, so let's not have anything that's just by memory, right? That's my goal, right? Let's not have anything that's just by memory, at least as minimal as possible. I want you to just have ideas and know how things work, right? The cosine, why is it positive over here? Because it's the x-coordinate. The x-coordinate is positive over here, it's negative over here, right? Right? The y-coordinate, it's positive up here, and it's negative down here, right? So the sine's going to be positive if you're up here, and it's going to be negative if you're down here, right? So it's more consistent rather than sort of like memorizing, oh yeah, I'm over here, so because for some reason, this should be negative. It's not some reason, it's because this is what the cosine is, and this is what the sine is. Right? Okay. So just to get rid of sort of arbitrary knowledge that was given to you and you didn't really, without really an explanation. Right? Why was it negative there? Because all students right? Take calculus? No. Okay. Right. Okay. Identities. Why is it true that cosine squared plus sine squared equals 1? Why is it completely obvious now that cosine squared plus sine squared always equals 1? When?
Because it's Pythagorean theorem because it's the unit circle.
Because we're on the unit circle, right? Because we're on the unit circle. Why? Cosine x, sine x, is on the unit circle. Right? The unit circle, we all use thetas, since I was using thetas earlier, is on the unit circle, namely x squared plus y squared equals 1. Right? So x squared plus y squared equals 1. Okay. 2, why is cosine of negative theta equal to cosine of theta? Why is cosine of negative theta equal to cosine of theta? Well, if I have an angle theta and I have an angle negative theta, what do I see about them? Well,
They have the same x.
they have the same x-coordinate. They have the same x-coordinate, right? They have the same x-coordinate because of picture. Right? These guys have the same x-coordinate, right? Same x-coordinate, right? What can you say about the sine of negative theta? What about the sines? What about the y-coordinates? What do you see? Are they the same? They are negative. They're negatives of each other, right? So negative sine theta, right? Again, because of the picture and some geometry, right? You know that this number is going to be negative of that number, right? Okay. Last example. Sine of theta plus pi over 2 equals cosine of theta. Why is that true? If this is theta, and this is pi over 2, right? So this is anyone see it? Reina, go ahead.
Okay, because if theta is 0, then it shifts like that, and
Theta is not 0. Theta is
Okay,
could be
never
anything.
mind then.
Theta could be anything. That's okay. That's okay. That's okay. Very good to be gutsy. Right? My Chinese teacher in college said the key to learning is shamelessness. Okay, so just say whatever you feel like, and I'll correct you. Yeah, Kayla.
Because theta ends up being the same as like the same portion of like the unit circle.
Elise.
Because cut out, but they were saying it's a 90-degree angle, so when it's shifting, when the whole 90 degrees is shifting, then it's the same.
That's the same thing there, right? And so what do you have? You have your similar triangles, right? And so what do you see? That if this is A comma B, right? What's this thing here? This is going to be negative B comma A, right? And so the cosine, right? The cosine of theta equals the sine of theta plus pi over 2. Right? Right? So why did all these things hold? Because of the definition, right? And just elementary geometric reasoning. Okay, that's it for today.